For this next homework assignment, we're going to work through plotting in MathCAD and also a little bit on some symbolic manipulation, calculus, that type of thing in MathCAD. So if you come down here, we have graphing and calculus. There's a couple worksheets there. Also go ahead and post this video there as well. But for now, we're going to come to the homework and then come on down to the symbolic manipulation plots and solve blocks. Okay, so here we have a couple expressions here that we're going to try to calculate, and then we'll also plot some of these as well. Okay, so in MathCAD, I have this open, this MathCAD 15. There's also the MathCAD Prime versions that work well as well. Okay, so let me go to just create problem number 1, and let's create f of x, just a new function, f of x equals x squared. Okay, so if we had to take the derivative of this, we'd know that is equal to 2 times x. But let's say it's too complicated or we don't remember how to do that. Then we can use this. If I just bring up this calculus toolbar, I'm going to be using that a lot, so I'm just going to drop it right here. I want to take the derivative. It's this first left one, and I do d f of x dx. Okay, so if I do df at 1, let's just do 1. That should equal 2 because that's equal to 2 times x. And I just plugged in x equals 1. Okay, so let's do the second derivative as well. I'll just call that d2f of x. And I can put in this second derivative here, f of x. Okay, and that's going to be 2. And then x. When you put in the 2, it puts it in both locations. Okay. Let me change this just a little bit so it's a little easier to see. I'll do 130. Okay, so I just zoomed in a little bit there. Okay, we could also symbolically calculate this df x, and then I use let's see, where is that? There it is, symbolically evaluate. Okay, and then that equals 2 times x. And if I want to do the same thing for d2f of x, and then symbolically evaluate. Okay, with the zoom, it kind of cuts it off, so I have to select it, and then it shows it again. Okay, so that equals 2. But let's go ahead and plot this. I want to create a new plot. I come up here to the plot or graph toolbar. I just insert this. Let me just go ahead and put x in here. It's gonna, and then I'll do f of x. Okay, so there is f of x, and then let me do df of x, and then put a comma if you need another one there, and then d2f of x. Okay, so it's going to calculate that and then come up with these values. If you want x to be over a certain range, you can do x equals 0, comma 1, and then hit the semicolon, and then you could go up to 10, for example. Okay, and then it'll show you from 0 to 10. There's just 10 points there, and if you double-click this, you can change some of the traces. You could have a line, maybe do a dashed line. There's some other things that you can change here. Symbol, for example, you could put a symbol in there. Okay, so there is f of x. Just double click that and it'll give you the plot. It'll be a little bit bigger when you do this. Part of the reason is that there's just a couple additional options, like you can change the scale here. Let's say I want to go to 200, between 0 and 200. It's very graphically driven here. Then I could change the scale on that as well. Okay, let's say I wanted to only go between 0 and 5 and 10, even though I have more data, then I can just show that data. Okay, so there is the first one. I just took a function, took the first derivative, second derivative, symbolically evaluated those, and then also plotted it as well. Okay, let's go on to part B. Well, actually, why don't you go ahead and try those, just part B and C there. Just go and replace that function, and then you'll get the different plots and different results there. Okay, so I did part A for you. Part B and C should follow pretty quickly there if you followed that. Okay, so let's go on to problem 2 now. So we have a function, and this one's going to be a function of f of x and y, and I have sine of x times cosine of y. Okay, so we want to evaluate the derivatives. Well, actually, let's go ahead and plot this first of all. Okay, just to see what it looks like. I'm going to insert a 3D plot here, and then down at the bottom I'm just going to put f there. And if I double click this, let me go to, I never quite remember where this is, but I want to show it as a color map. Fill. Okay, let me try that. Okay, so there it is right there. I've got my 3D plot. This is what this looks like, this function looks like, and then I could evaluate it at, I want to go to 1, 1, and evaluate it there. Okay, so let me evaluate the derivative there. So this one is going to be, one of the ways I can do this is just x equals 1 and y equals 1. Okay, and then if I just say, evaluate the derivative with respect to x, let's see, what is the question asking? Evaluate the derivatives at x equals 1 and y equals 1. Okay, so I've got a double derivative here. Y, I'll put f of x comma y here. Okay, and then there is, there it is right there. Okay, so I took the derivative with respect to y first. If I change this, okay, let me move this one down just a little bit so it doesn't get in our way. It's kind of hard to select this sometimes until the black hand appears, and then you can drag it down. Oh, I almost had it. Oh, it doesn't want to let me do that. Okay, so make that a little bit smaller. I cannot. Okay, there it goes. It moved for me. Okay, so if I wanted to change the order here, differentiate with respect to x first and then y, I get the same answer. Okay, so I have the, I could do this as well with, nth order type thing. So if I put this in here, f of x, y, okay, and then the first thing that I want to do is maybe x second and then y. Okay, so there is my derivative there. If I wanted to swap those, you can check to make sure it's going to be work the same way. There, I'll do y, f of x, y, okay, and then put an x here and a 2. Okay, so this is the same answer. Okay, so it doesn't matter which order you do it in for this one. Okay, and then try to do part C as well. All right, let's go down to the next one. All right, I'll go ahead and save this and evaluate each of the following indefinite integrals. I'm going to, okay, so now we did derivatives, now we're moving on to integrals. Okay, so this is going to be problem 3. Okay, so come over here to my calculus toolbar. I'll go ahead and close some of these. This calculus toolbar, okay, again, it's this one right there. I want to do an indefinite integral. Okay, so I just do a, if I need to put a parenthesis there, I can open parenthesis, close, or I can hit the single quote as well. a plus b times x plus c times x squared, and I want to evaluate this, and I want to do it maybe symbolically. Okay, so if let's come up here to symbolics, evaluate, oh, there it was. Okay, so evaluate symbolically, and then it came up with this. I think I can also take this one right here if I just want to have this be an output, and then come over here to the evaluate toolbar, and then evaluate this symbolically. You know what? I think I had x equals 1 there, so that didn't work too well. X was defined as 1 from an earlier one. So go ahead and just do this symbolics, evaluate symbolically, and let me select the whole thing first. Okay, it's just going to insert it below that, evaluate symbolically. Okay, so there is your integral right there. Okay, so that's essentially what we're doing here. We're just typing in these integrals, these indefinite integrals, and then we go up to the symbolics and then evaluate symbolically. Let's just go and do the next one. Okay, so we'll go ahead and put in 2 times x squared times y. Okay, and I need a double integral here, so I'm going to go ahead and add 2 of them. Okay, I'll just do this. 2 times x squared times y, and then I'll integrate with respect to x first and then y. Select the whole thing by hitting the space bar, and then come up to symbolics, evaluate, and evaluate that symbolically. It'll put it right underneath. Okay, so there it is right there. There's the answer to the double integral. Okay, so let's go on to the next one. Now we have some definite integrals versus indefinite. Definite meaning just we have the limits of integration, and okay, so let me go ahead and do this, problem 4, and I'll make a little extra room for myself. Okay, so indefinite integrals, you select the one over here that has the a and the b, the little icon there up in the integration or the calculus toolbar, and then this one is 1 over x. Okay, and then I have dx, and I want to go from x a to x b. Okay, just x, then hit dot b to get subscript. Okay, and let's go ahead and just try to evaluate this one symbolically. Okay, so there's this, depending on what a and b are, it'll produce a different result. So it'll be natural log of xb minus natural log of xa if xa is greater than 0 and xb is greater than 0 as well. We can't have the natural log of 0. Okay, so otherwise it's going to be undefined. All right, so that would be like an if statement like we saw in a previous video. I'm going to go just delete that one. Okay. Actually, I'll leave it there. Okay. All right, and if you knew that xa and b were going to be greater than 0, you could just take that out and say it's natural log of xb minus natural log of xa. Okay, let's go on to part B now. Okay, so we have a double, actually it's a triple definite integral. So let's go ahead and just put 3 of these in here. Okay, just type it 3 times r. Okay, and then we want to integrate with respect to r, and then theta, type t, and then control G. No, it's q. Okay, q, and then control G. Okay, and then z. Okay, and then we are going to be integrating from 0 to capital R, and then from 0 to 2 times and then type P, and then Control G. That gives you 2 pi. And then this one, do 0 to h. Okay, so this is all going to be symbolically evaluated. Evaluate symbolically. There's also a shortcut key there. I think that was Shift F9 if you have it selected. Okay, so there is our volume of a cylinder. Okay, so we just integrated throughout the radius, and then the radially, in terms of the angle, and then also the height. Okay, so we want to evaluate for the next one, number 5, evaluate each of the following definite integrals. Okay, so we have, I'll just show you the first one. I'll let you try the other ones as well. Actually, C, I want to show you a little bit on C. I'll do A and C for this one, problem 5. Okay, so for the first one, okay, this one's easy. You should know how to do this. This is e to the x dx, and then if you put in, now I'm going to be putting in numbers here to my integral 0 to 1. Okay, and then I just get e to the 1. Actually, that is, no, that is not e to the 1. Okay, so that is, yes, that is going to be e to the 1 minus e to the 0. Okay, so there it is, the same answer if I integrated it. Okay, versus the analytic solution to it. Okay, so let's go on to C, because I just wanted to show you one thing. We can also put in units here. Now this is by default in radians, but if I had some units that I'm going to do the arc sine of x dx, and I want to go from 0 degrees to 1 degree. Okay, and the way I do that is I put in, normally this is in radians, but I just want to do it in degrees. Okay, so 0 degree, from 0 degree to 1 degree. Okay, so there is the answer. If you left that off, you'd get a different answer because it's by default in radians. And so just make sure if you want to do it in degrees, for example, just integrate from 0 to 1. 0 doesn't matter because it's 0. Okay, so let's go on to the next one now. We have one more that's going to be about plotting, and then we have from 7 on we're going to be doing the roots and solve. I'll do a separate video from 7 on, but let's go and do problem 6, and then problem 6. Okay, so a couple things that we need to define for problem 6 are just these. Let me come back up here. Just the A. Let me just go ahead and define this one. This is a heat capacity correlation. Comes from the Dipper database, and the heat capacity of ethane. So we just want to plot this from the freezing to the melting point, and just do a couple other things with this correlation. So go ahead and just type in your A, B. Okay, and then we have C. You'll see a little green there. It means that I've overwritten amps and coulombs. We're not going to be doing much with electrical stuff today, so I'm okay with that. Normally I don't like to redefine built-in units. Okay, and then E is going to be 7.5287 times 10 to the second. Okay, so there I've got my coefficients there. Let's go ahead and create a new function. Okay, and then I also need one other thing. I'll just go ahead and make sure kilomoles is defined as 1,000 moles. Okay, so that is not in there already, but I'm going to need it in my... Okay, so I've got Cp as a function of temperature, and that's going to be A plus B times, and then I put a single quote to get the parentheses there, Okay, then I have c divided by t. If I hit spacebar, then it's going to select c divided by t, and then I can divide that by the hyperbolic sign of c divided by t, spacebar, close parenthesis, and then spacebar a couple times to select that, and then I want to square it. Okay, if I want to give myself a little bit more room, I can put my red arrow there and hit enter a couple times, and it'll scroll down. Okay, so okay, let's keep going with this. Plus d times. Okay, so I'm just going to put this one in. Make sure you have your parentheses correct here. Okay, and then that is going to be all of this. If I hit the single quote, it'll put a parenthesis around it, and I'm going to multiply it by joules per kilomole times Kelvin. Okay, so I've got this, but the temperature input, okay, I don't have that what the units are. So I'm just going to divide this by Kelvin. So whatever temperature I put in, it's just going to divide it by Kelvin and put it into the right units for me. Okay, so now I have C sub p, and I can just evaluate this. C sub p at 300 Kelvin. Okay, so that's going to give me joules per kilomole Kelvin. Okay, so there I can see the value. But what I want to do is have temperature defined between a certain range here. So temperature, I could say it's 90 times Kelvin, and then do a comma, and I'll go to 91 times Kelvin, and then hit the semicolon, and I want to go up to 305 times Kelvin. Okay, so if I just say temperature equals, it's going to show me that vector, okay, of values. But let's just go ahead and plot this. Okay, so we want to create a plot. So I'll give myself just a little bit more room here. Okay, so plot, graph, and I have temperature, and then I have on the y-axis this little black box, C sub p of temperature. Okay, so it shows me temperature in Kelvin versus my heat capacity, and that is going to be in joules per mole Kelvin. But if I wanted to change the units on that, I would just divide this by joules per kilomole Kelvin. Okay, and it would show it to me in different units. If I wanted to show this one in, let's say, ranking, okay. Let's say I wanted to show it in Kelvin instead. Okay, so there I have my plot. So let's say I want to show the value at 200. You can change this. You could add a line to it. And show the value at a particular point. Okay, so I want to come up with, now I want to have part B. Let's see. Heat needed to raise the temperature of a low pressure gas can be obtained by integrating the heat capacity from initial to final temperature. Calculate the heat needed to raise 7.5 moles of ethane from an initial temperature of 200 to 500. Okay, so now we just get to integrate this C sub p function. So we have number of moles is going to be 7.5 moles, and T1 is equal to 200 Kelvin, and T2 is going to be equal to 500 Kelvin. Okay, so I'm just defining these here so that it's going to simplify this expression. So I have the number of moles times, and then I'm going to integrate, and I'll integrate this C sub p of T, and I'll just put this T right here, and I'm going to integrate from T1 to T2. Okay, so Q equals, okay, there's the number of joules that it took to raise 7.5 moles of ethane from 200 to 500 Kelvin. Okay, so that concludes this. Just basically a brief overview of what we've done. We did so a little bit of plotting. We did a little bit of derivatives, calculus. We did symbolic, exact. And then we solved a chemical engineering problem here where we just wanted to integrate this function from 200 to 500 Kelvin. For the next one, I'll go ahead and go on to this root finding one and some of the iterative solving capabilities of MathCAD.